Thank you all for joining us. We're going to give everyone just a few minutes to settle into the room and then we'll get started. All right, good afternoon, and thank you for joining us for session 3 in our Applying the Safe System Approach for Rural Half-Day Virtual Mini Conference. My name is Jaime Sullivan. I am the Director for the National Center for Rural Road Safety, and we're excited that you're here to join us for this session 3, which will be on safer roads in the rural context. I have just a few logistics for you all. This session 3, will be an hour and a half long. To activate closed captions for the webinar, you can click on the Show Captions button, which you can see on the top right of my slide. It will be shown at the bottom of your screen. You can also use the arrow there to adjust captions under the caption settings at that same button. As I mentioned, we are recording today's webinar for website archival. In about a week, you'll be able to find this on both our webinar archive page as well as on the virtual mini conference page as well on our website. We will be using our chat pod today for some discussion with you all. So we would ask if you do have any questions, if you could please make sure to put those in the Q&A pod at any time while our presenters are speaking. We'll stop 3 times today to answer those questions. You can also use that Q&A pod as an easier way to alert organizers of any technical difficulties you may have with today's Zoom. We do have handouts available for download, and those will be dropped periodically throughout today's webinar in the chat pod, so you can take a look for that link and download those if you're interested in a copy of the handouts. At the end of today's webinar, we will provide a feedback form to you as well. As I mentioned, this is a new thing that we're trying with this virtual mini conference. We'd love your feedback on whether or not you like how this worked out, if you liked having the separate sessions, and if you did like it and you'd like us to do it again in the future, what kind of topics you might want to see us do for this mini conference. We will, as always, have certificates of completion available. They take about 4 to 6 weeks to hit your inbox. When you do receive those, in the email body, there will also be a link in case you need to apply for the more formal EUs that Montana State University can provide for you. We have 3 presenters today, and they will be talking to you about Federal Highway Administration Safe System Approach Design Hierarchy, understanding self-explaining road design as it relates to suburban to rural facility transition zones, and then also on using crash data and kinetic energy principles to prioritize intersections for safety improvement. So unfortunately, our first speaker was not able to join us at the last minute. So we do have still some slides because I feel like the Safe System Design Hierarchy is a very important resource, and we wanted to make sure that you've heard about it if you had not already. So I'm going to go ahead and go through these slides for you. Again, I'm Jaime Sullivan. I'm the director for the National Center for Rural Road Safety. I'm also a senior research engineer at the Western Transportation Institute at Montana State University, and I'm a licensed engineer in the state of Montana. So before we go through the hierarchy itself, I did want to talk to you all a little bit about some general information to keep in mind about the safe system approach and using it for rural roads. The National Center for Rural Road Safety has been conducting some forums on the safe system approach for rural to see if we could really come up with some good information to provide to our audience, as well as some case studies and examples. And there's a few key things that keep coming up out of these forums that we've been having that I wanted to make sure I brought up for you all before we do our presentations today. So when we think about the safe system approach and how we're applying it, we need to continue to remember that it's a holistic approach, and it's also iterative, just with any other safety that we're doing. So on our roadways, as things change, so can how we look at the safety of those roadways. So when we have modal changes or add additional modes to our roadways, as our road users change, as the land use around our roads change, or even the context of our roadways. So whether that be with different weather situations that we may have, tourism uses on our roadways with a lot of non-locals using them, or even growth changes for how many people are using our roadways. We need to continue to take a look at the safety of them and how the safe system approach applies to them, as all of these different changes can have an impact on how we're going to look at that. Additionally, in rural areas, one of the things we keep hearing from our audience is that it is an opportunity for collaborations, especially in rural where there is a lack of funding and resources. And this really hits on the principle of the safe system approach of it being a shared responsibility. So as all of us are working, this large number of us are working to decrease fatalities, it leads to an opportunity for these collaborations. And we all really need to take a look at our contact sheets that we have in our jurisdictions and build a bigger network, making sure that we're collaborating outside of our departments and including more people at the safety tables as we're taking a look at what countermeasures and solutions we can have. And this was discussed a little bit more this morning as well. In session 1, you may have heard David Ederer talk a little bit about road safety audits and how he feels it's really important that we make sure law enforcement and epidemiologists are also invited to those so that they can provide their input and a different view shed into what could be helpful in a road safety audit. And then you may have also heard in session 2, Brandy Brubaker talked a little bit about how they are implementing coalitions in their area so that they can make sure that they're sharing the information as well. Another thing to keep in mind that we keep hearing is that all elements of the safe system approach, which are those 5 that you see in the center of the circle on the slide, they really all tie together, and you can influence each of the elements through another element. And you'll hear that through the 3 presentations you're going to have today, because while we're talking about the safer roads element, you'll hear us talk about some of these other ones, how road user behaviors or how post-crash care or speeds and vehicles all can help implement or affect the other pieces, and how some of our solutions can help and affect those other pieces as well. So when we talk about in rural as well, and what some of the success stories for safe system approach have been, many of those successes are pointing to not only implementing proven safety countermeasures, but also making sure that there's the systemic implementation of these countermeasures. And with the systemic implementation of them, we're not looking just at hotspots. As we know, in rural areas, crashes are not always in the same location. And so looking at this from a systemic point of view really helps us be able to be proactive, which is one of the principles for the safe system approach. Systemic means that we're taking a look at the risk factors of a particular roadway that is being an issue, and then examining the other roads in our jurisdiction to see if they have those same exact risk factors. And if they do, when we apply countermeasures, we're going to apply those countermeasures to those other roads with the same risk factors, even before a crash may have happened. And this is what's making it proactive for implementing that safety piece. So I do want to point out these 2 resources that are on the slide right now. I wanted to make sure that everyone was aware of these. They are both created specifically for rural communities. The very first one takes Federal Highway Administration's proven safety countermeasures and talks about the ones that are most specific to rural and gives very rural examples for how they're being implemented in rural communities. And the one on the bottom is NHTSA's traffic safety countermeasures that work in rural communities. And same thing, they've taken the longer list that NHTSA has of all of their traffic safety countermeasures, and they've provided those ones that are specific for rural and provided case studies for how they are being implemented in rural areas. As with always, we're looking for, as are you looking for, case studies of how people are putting safe system approach into practice and what those rural success stories are. So I do want to encourage you that while we're going through these 3 presentations today, in the chat pod, we'd love to see some examples of how you've applied the safe system approach in your jurisdictions and what you feel are some of the success stories and lessons learned as well. Really make sure you're using that chat pod to share with each other. So the Safe System Roadway Design Hierarchy Guide can be found at this QR code. And we're going to go through it a little bit more in detail. But what it is a framework for evaluating those countermeasures and strategies that we just talked about, and really looking at them and how they align with the safe system approach, both from the principles, which are the 6 that are along the outside of the safe system approach graphic that I showed, as well as those 5 elements that were on the inside. The alignment with the safe system approach can be dependent on context, classification, location, and users of the facility. So we want to take a look at all of those when we're looking at how it aligns with them. And we also need to note that some of the countermeasures can be applied for the safe system alignment in different contexts in different ways, even if we're using the same exact countermeasure. And we'll go through some examples of what that could look like. It's important to note that this hierarchy that they've created is a supplement to other tools you may already be using for identifying, selecting, and prioritizing countermeasures. It's still important to make sure that we're using those other ones that we typically do. So your community input, your feasibility, cost, the extent for potential crash reduction, project readiness, funding availability. So this is just one more of those pieces to help you prioritize when you're looking to do so. The hierarchy, as you can see over on the right in this graphic, is split into 4 different tiers. Those tiers include removing severe conflicts, reducing vehicle speeds, managing conflicts in time, and increasing attentiveness and awareness. We're going to go through each one of these in a little bit of detail. So the very first one is to remove severe conflicts, and this fits back into the safe system approach principle that humans are vulnerable. And we do have our speaker, Jeff, who's going to speak later, is going to talk a little bit more about kinetic energy and how these severe conflicts could affect humans in their vulnerability as well. So in this first one, we're looking at strategies that are going to minimize these conflicts and possibly create fatalities and serious injuries. We do this in a few ways. We can do this by separating road users who are moving at different speeds. The most common example that we hear for this would be a vehicle and bikes or pedestrians that are moving at different speeds. But in a rural area, another example that we could look at would be vehicles and something such as our horse and buggies that are also using the same roadway, or our agricultural vehicles. We can also look at this as separating road users that are going in different directions in the same space as well. And then we also can look at it from the perspective of our rural roadway departures too. So some of the examples of what we could put into place in countermeasures for this tier 1 would be things such as our roadway design improvements at curves. In rural, we know that horizontal curves are associated with about 27% of all fatal crashes, and around 80% of those are rural roadway departures. So being able to implement these roadside design improvements at curves can really help us to reduce the total number of crashes as well as the fatalities and serious injuries at them as well. Some of these types of design improvements could be things such as vegetation management, removing roadside objects, flattening of side slopes, widening of shoulders, or installing roadside barriers. Another example of how to remove severe conflicts could be roundabouts. And we've heard a lot about these going into rural areas as well. And on our archived webinar page, where you're going to be able to find the recordings for this and the other 2 sessions, you can also find some recordings of webinars that we've had about rural roundabouts and how they really are impactful for rural areas. In a typical intersection, there's going to be 32 conflict points. And when we put in a roundabout, we are going to reduce that to 8 conflict points. So this can minimize that as well. In addition, as we talked about earlier, where we have countermeasures that cross over tiers in this hierarchy or cross over the different elements, roundabouts really help with the speed piece as well, because it reduces the speed of the vehicles. So an example, as we talked about with the separating our road users, such as vehicles from our horse and buggies. An example would be in Ohio, where they have taken some of their roadways and expanded the shoulders of the roadways to make them wider so that the horses and buggies are not in the same exact travel lane as the vehicles, in order to separate the speed differential and remove some of these severe conflicts. If any of you all have other ways that you're using Tier 1 and removing severe conflicts in your jurisdiction, again, we'd love to see those in the chat pod right now. Drop in some of the ways that you may be doing this. Tier 2 is to reduce vehicle speeds. This one, we're going to use design features and speed management strategies for this tier. And we're really trying to reduce the kinetic energy if a crash occurs, to make sure that the severity of our crash is not as bad. As I mentioned earlier, Jeff is going to talk a little bit about kinetic energy in his presentation. And some of the examples here of how we can accomplish Tier 2 and reducing vehicle speeds in rural areas would be variable speed limits. One example for this one would be in Colorado, where they are adjusting speed limits in real time depending on the road conditions, in order to increase the safety for their motorists. So they're doing this in examples of winter weather or even in high winds to try and reduce some of the severity of crashes. Another example would be gateway treatments, and these could be physical features or landmarks that are used to clearly convey that the context of a roadway is going to change. And I know Wes in his presentation is going to be talking about transition zones, and so we may see some examples of gateway treatments in his presentation as well. And lastly, self-enforcing roads is another way to reduce vehicle speeds. And Wes definitely will be talking about this piece in his next presentation as well. Tier 3 in this hierarchy goes through how to manage conflicts in time. And this is when we cannot separate our road users into different spaces. In Tier 3, this is when they have to occupy the same physical space. And so how can we make the time change for them to reduce some of this severity? In order to do this, we're going to use traffic control devices to minimize these conflicts. And a couple of examples that could be used for this would be left turn phasing in our traffic signals, so that we do not have vehicles turning left at the same time that we have pedestrians crossing the roadway. We could also use this for our emergency vehicle preemption. We talked a little bit earlier about post-crash care. This would help with a post-crash care piece and would help to reduce intersection crossing conflicts, reduce clearance times, and also make it safer for first responders as we decrease the crash rates associated with first responders in the emergency vehicles. Pedestrian hybrid beacons are also another example of how we can manage these conflicts in time between pedestrians and vehicles. And lastly, Tier 4 is where we can increase attentiveness and awareness. In this tier, we're really working towards alerting roadway users to certain conflicts that can occur, and then providing them with appropriate actions to take that are consistent with the safe system approach. So some of the rural examples that we have for this one would be to implement wider edge lines. So typical edge lines are 4 inches, and in wider edge lines, we're going to move those to 6 inches instead. This is a low-cost countermeasure that improves visibility of travel lane boundaries. Commonly, they're installed on rural 2-lane highways, particularly those that have a history of single vehicle roadway departure crashes. And these wider edge lines can help with things such as speed, if there's no lighting, being able to see better, undivided roadways, and then also horizontal curves that we know are so risky in rural areas. Going from 4 to 6 inch wide edge lines has been shown to have a 37% reduction in fatal and injury crashes on rural 2-lane roads. Another example for increasing attentiveness and awareness that we all know about would be the rumble strips and rumble stripes that can be used to alert drivers that they are crossing an edge line or the center line in the case of a head-on collision. And then lastly, another example that we can point to for Tier 4 is the systemic application of multiple low-cost countermeasures at stop-controlled intersections. And this is what we're showing in the graphic on the slide here, where they have double stop signs, double stop ahead signs, the stop sign bar, and the pavement markings as well. Louisiana DOT is using this particular countermeasure. They installed this low-cost safety treatment at 89 stop-controlled intersections, and they found a 56% reduction at three-legged intersections and a 64% reduction at four-legged intersections of their fatal and injury crashes. Something else you can consider with this as well that's low-cost that others have done is to put reflective stripes on their signposts as well for greater visibility. So just to wrap this up about the hierarchy, so how do we use the hierarchy? Now that we know what those different tiers are, it's a framework for evaluating these countermeasures for how they align with the safe system approach, as I mentioned before. And we can use this either as a project-based site assessment tool to look at each individual location, or you can use it for planning phases for prioritizing your criteria, such as using it as a prioritization tool when you're thinking about your local road safety plans or safety action plans, and also in the road safety assessments and audits that we talked about earlier. When you're doing this, it's suggested that you consider Tier 1 first, as the Tier 1 countermeasures are those that include physical separation, and that means it's a permanent elimination of the conflict itself. The other tiers would still have those conflicts there, just not as severe. Subsequent tiers, if you're looking at tiers 2, 3, and 4, can either be used alone, or you could use them in combination with each other. And that combination really reinforces the principle of the safe system approach, that redundancy is crucial. There also are some countermeasures that cross-cut multiple tiers, and I'm going to switch the slide real quick here. This is a table pulled right from the report. There are two of these tables in there for you to take a look at, but you can see these columns show each of the tiers that exist, Tier 1 through 4, and those check marks are showing you which tiers that they go with. So the roundabouts, for example, is both Tier 1 for removing severe conflicts and Tier 2 for reducing vehicle speeds. And at the bottom here, you can see our local road safety plans and our road safety audits have the possibility of hitting all 4 tiers. This is also can be used as an incremental approach. So if you do not have enough funding to do some of the things in Tier 1, you can choose some of the lower tier options as a temporary solution until you can have the funding or the ability to build some of these permanent solutions and put them into place as well. So again, I am going to leave you with the QR code for the safe system roadway design hierarchy. Again, I apologize that our speaker was unable to make it, but we did want to make sure that you were able to hear a little bit more about this guide and know that it existed and be able to use it as you work towards prioritizing your countermeasures for the safe system approach. Right, I'm just going to check real quick and see if we have any questions. And I do not see any. So I am going to go ahead and stop sharing. Again, I do want to encourage you all that if you have any examples of how you all are applying either the hierarchy itself or any of the safe system approach pieces or any countermeasures, please drop those in the chat pod. We would absolutely love to hear from you all as well. But now I am going to turn our presentation over to Wes Kumfer. He is a Senior Engineering Research Associate at the Highway Safety Research Center at the University of North Carolina with a wealth of experience in crash data analysis, the safe system approach, education, and workforce development. Through work with FHWA and NHTSA, he has contributed important knowledge to the state of the practice on topics like speed management, safe system approach, pedestrian and bicyclist safety, and behavioral countermeasures. Prior to joining HSRC, Wes earned his Ph.D. in civil engineering at Texas Tech University, where he taught courses in transportation engineering and highway safety. Wes is also a certified level 1 road safety professional, and I'm really excited to turn it over now to Wes, who's going to talk about self-explaining roads.
Sorry, I was still muted. Thank you so much, Jamie. I really appreciate it. And can you confirm that you can see my slides?
We can.
Great. Thank you all so much. Really, Jamie did a great job of setting the stage for what I'm going to talk about. So, I'm going to start out just with an exploration of what it is that we mean by self-explaining roads. But I'm using this conversation as a little bit of a Trojan horse to talk about human behavior because I think this is one of the most important concepts that we, as practitioners and professionals who are trying to prevent crashes, can really wrap our heads around it. It's beneficial if we understand why people choose to make the decisions that they do, if they make a choice, caveat. Um, in interacting with our roadways because I think that will give us a better understanding of, how we can manage kinetic energy. And then I'm going to explain the role that roadway design has in driver speed selection. And then ultimately, we're going to circle back to this concept of a self-explaining road. And as Jamie talked about, we're going to look at some different things that we can do to try to reduce speeds and provide some self-explaining roads. So, just to start out, let's explore this idea of what I mean by self-explaining road. And you may have heard a term, self-enforcing road, sometimes is used as a synonym for this. But really, the definition that we see in the research, especially from a researcher named Jan Theeuwis, who is kind of the father of this concept, uh, lays out the idea that a road or a self-explaining road is a road that aligns roadway design with an intuitive understanding of appropriate driving. And so, what this can mean is that a self-explaining road should guide users to an appropriate speed or other driver behavior without the need for enforcement or extraneous signage. And so, whenever we're talking about the safe system approach and we're thinking about how it is that we can prevent crashes, a lot of times this question comes up when people look at the wheel and they think, well, where does enforcement fit into all of this? And maybe that's led to a little bit of siloing unintentionally with the roadway people saying, well, we just need to, work on our safer roads, and then enforcement just feels like they're only allowed to enforce speeds. I would argue that the ultimate goal of the safe system approach is to produce what's called a safe system. That makes sense, right? And ideally, that means that we would have roadways that would be so self-explaining and self-enforcing that really we would only need traffic enforcement for very egregious behaviors. And what I mean by egregious would be speeds well in excess of the speed limit. The idea being that within a safe system, the roadways should generally be so intuitive and so understandable to road users that they just sort of naturally drive in a way that is safe and that is going to prevent kinetic energy and roadway death and injury. That may seem like a tall order, and I would agree with you on that. I think we have a lot of work to do in order to get to that goal. But moving in that direction, let's think a little bit more about what it is that would be intuitive for drivers. And again, TOS, who I said is kind of the father of this concept, has identified three different ways that we can identify a self-explaining road. So those roads that have the same function, the same speed profile, the same type of road users should look similar. Meaning that wherever you are driving, if a road is meant to provide a certain function, and ideally facilitate the same kind of speed, it should basically look the same no matter where in the country you are. I would argue that right now in the United States, we do not have easily recognizable roads based on this principle. The next one would be that we have easily distinguishable roads. So roads of different categories should look differently. In other words, there should be clear differences in appearance and layout between roads that belong to different road categories. Now, I was looking at the chat and saw that we have a few people from different disciplines in here, but I'm curious for those of you who are engineers, if you've ever been puzzling over a roadway map and trying to think, well, is this one a collector or is this an arterial? Or is it a local road? Do you ever have trouble distinguishing between what should be different functional categories? Because if so, that could mean that you're not dealing with easily distinguishable roadways. And then the third category the third distinguisher that TWES lays out would be easily interpretable. And that would be it should be clear from the design what the desired behavior should be on that route. The road characteristics should induce this type of behavior. Again, it could be speed. It could also be, making sure that people are watching out for pedestrians or bicyclists, that they come to understand who's going to be interacting on a roadway and maybe yielding at certain crossings, that kind of thing. So I'd like to maybe transition a little bit and open up the chat if anyone would like to respond to this question. I am keeping an eye on the chat pod here, so I appreciate your responses so far. But think of a roadway that is somewhere near you, and you can just pick some roadway that you drive on all the time. And do you think that roadway is self-explaining and why or why not? So while you're thinking about that and maybe putting a response in the chat pod, I'm going to show you a roadway that is near me. So I would say, kind of a suburban roadway. It actually leads out to some rural roadways that are not too far from me. For those of you who are unfamiliar with Chapel Hill, I would say I like to tell people we're a fake city. We're a college town, but we do have a few big arterials. Um, and generally speaking, it's kind of a mix of suburban and rural with only a few kind of real urban designs here and there. I'm seeing a lot of people saying that no, they don't have self-explaining roads. Um, I'm glad to see that in the chat. I'm not happy to hear that that is the reality that you live with. Yeah, and most of your rural towns you would argue are not. So looking at this example right here, this is the Weaver Dairy extension that was kind of intended to link one of the bigger arterials in our road or in our sit town. And I use big arterial somewhat loosely there to sort of some of the rural area. And I asked myself, do I think this roadway is easily recognizable? And, if I'm trying to go down this road, I might ask, who does this road serve? Is it pedestrians, bicyclists, and drivers? Well, I do see a bike lane on it, and there are actually several pedestrian crossings that have rectangular rapid flashing beacons. So I don't know, maybe it's supposed to be a low volume access road? Is it easily distinguishable? So do I know what the function of this roadway is? And is it wide? How much traffic does it carry? I will say, with my experience driving on this road, is it feels very, very wide. It does not feel like an access road that is going to have a lot of pedestrians and bicyclists on it. And in that case, I might argue, I don't know if this is easily interpretable. So based on just this cross section, this shot from Google Earth, Google Street View, I'm curious, what speed limit do y'all think this road is probably signed at? 30, 35, 35? Yeah. So 35 would have been my guess. So I'm about to maybe trick you a little bit, but this roadway is actually signed at 25 miles per hour. So, people do not drive 25 miles per hour on this road. I can tell you that right now. They're hauling on it. People generally driving 35 to 40 on it. I see some of you are like, what? Or wow, that is too wide of a lane. I would agree with you. And the reason I think this road is perhaps over designed is because, there is a fire department at one end of it, and I think they probably designed the road to meet the needs of fire trucks pulling into that fire department. But unfortunately, what this means is that for the entire stretch of the rest of the road, you have people who are going to be driving well in excess of 25 miles per hour. And yes, one might say under designed. Yeah, you might have people driving well in excess of 25 miles per hour while pedestrians are trying to cross those RFBs, while bicyclists are riding on it. I don't think this is a self-explaining road. And so I think we have failed to take into account how people are intuitively going to navigate this roadway. And so the researchers who have really dug into this concept of self-explaining roads a lot, they would argue that while some countries, US I would say is one of them, have a range of different functional classifications, they would probably argue toward a much narrower view of roadway functional classification, where really you sort of have very discrete designs. You have through roads. These would be what we might think of as our freeways. They provide the highest mobility and limited access. You have your distributor roads, or what we might think of as collectors, which are literally just to transmit people from those through roads to access roads. And then those access roads, which should give us door-to-door access. And while we do have all three of these kinds of roadways in the US, I would say one of the big problems we have is in the big arterials and in that transition, especially with rural areas, trying to go from things that are functioning like through roads and suddenly you hit a town and you're functioning as an access road. And we have to figure out how do we get people to change and intuit that change in design if we are going to design those kinds of roadways. So it's definitely a challenge. Yeah. So let's go ahead and take another look at that definition of a self-explaining road because I do want to clue in on this concept of a roadway being intuitive or not. And I was looking at the chat earlier and I saw that someone in this chat is a psychologist. So I am going to be calling upon some psychology here. Please don't, grill me too hard if you feel I'm not representing psychology correctly. But I do think it's really important for us to recognize how it is that people actually make decisions. And so, why is it that people are going to, for example, select a speed? And one way to think about this is that a lot of the research in psychology has shown that human beings make decisions in two different ways, that we're guided by two different systems. We often assume when we're designing our roadways that people are going to be rational actors and they're just going to follow whatever our posted speed limits are, for example. But that's really not always the case. We also know that people are influenced by the environment. And then one of the fundamental aspects for the safe system approach is that people are going to make mistakes because we have lapses in attention, for example. One thing we know for a fact is that driving is a very cognitive demanding task. And because of that, people cannot maintain attention for a long period of time. Um, just a little bit of a side note, I recognize I don't have a big a slide here, and I don't want to get too far off topic, but I frequently talk with people today, and when we try to diagnose why do crashes occur, and I'll often hear someone say, "Well, it's because everyone has cell phones now." And while I do think that cell phones contribute to inattention on the roadway, I would also argue, and other researchers have made this argument, that driver distraction has been a thing for a very long period of time. And I think we're kind of missing a bigger picture if we only zero in on cell phones rather than the entire system of the need to drive long distances within a demanding work schedule with a lot of other things in our mind and potentially even respond to, say, our job emails or phone calls, maybe be on a meeting over Zoom or something while we're driving. I think we're not setting people up for success by asking them to drive and do anything else, whether or not it's a cell phone. So, do I think distraction is a problem? Yes. Do I think it is the only problem? I think trying to cure distraction is kind of missing the point. But to get back to this question of human psychology and human behavior, one thing we know about people is that we make decisions both deliberatively and intuitively. Some of you may have been experienced or may have seen the Daniel Kahneman book where he talks about slow thinking and fast thinking. But really, we have a lot of decisions that we make during a day that we don't actually consciously choose. We just sort of go with our gut instinct. These would be intuitive decisions. So a lot of times, if we're going and just I don't know, driving somewhere and we kind of zone out and we're like, well, how did I get home? A lot of times we zoned out on the roadway because we have so much experience driving that it becomes an intuitive process. A deliberative process might be if you're traveling somewhere new and you have to actually actively plan out a route, which is something of a lost art now since most of us are probably using our smartphones or Android Auto or whatever to navigate. But a lot of us are not, if we're following routine driving behaviors, are not actually actively choosing much about the process. We're just sort of following our instincts. And because of that, when we assume that people are going to be rational decision makers, what we assume then is that if we just tell them to behave in a certain way, such as, hey, obey the speed limit, we think that that's going to produce a desired behavior of them not speeding. Uh, speed limits appeal to that deliberative rather than the intuitive system. And we see that problem when we look at roadways like that Weaver Dairy extension I was showing you a little bit ago. All of you were like 35 miles per hour, 45 miles per hour, 50 miles per hour, because that is the speed that you think that road would intuitively lead you to select. It being signed at 25 miles per hour tells us that the engineers or planners or whomever, set that speed limit is um, that we are, telling them they have to deliberatively choose to slow down because that is not the direction that the actual design would be taking them. And then I think a lot of this sort of deliberative decision making is built into our codes for roadway design. This is a screen cap from the previous version of the manual on uniform traffic control devices, but this whole idea that is codified in the way that we design our roadways is that people are going to be reasonable and prudent. And I see a comment in the chat about drivers and pedestrians and bicyclists and sharing responsibility. Yeah, and the idea is that everyone's going to be reasonable and prudent, and it puts a lot of that need for reason and prudence on the pedestrian, right? So, moving on a little bit though, if we recognize that we're sort of asking a lot of drivers and maybe not letting them drive on roadways that intuitively tell them the speed we should select, that's setting them up for situations where they're going to be involved in crashes and be exposed to dangerous kinetic energy. And I know Jeff is going to be talking a lot about kinetic energy, and Jamie just gave you an introduction to it, so I don't need to belabor these points too much. But I would be remiss if I did not tell you and remind you that kinetic energy is dangerous. So, the equation, if you haven't seen it before, if you've seen me give a webinar before, you probably have because I beat this drum all the time. Kinetic energy is 1/2 mass times velocity squared. That means that the speed is the killer in our crashes, right? So we need roadways that intuitively guide drivers to lower speeds. And I think that particular explanation for why speed is so important is why we see some of the trends that we have that I'm going to show you over the next several slides when it comes to traffic fatalities in the United States. We know that for those who are inside vehicles, safety has nominally been improving. We know that really cars and large trucks are designed much more safely than they used to be, and that probably has driven a lot of that occupant protection down. But as pedestrians and cyclists are more exposed to high kinetic energy, more people are dying on our roadways. And we know that about 50%, I think, maybe the majority of pedestrian fatalities occur at night in the dark. And that is a location where someone is going to have a hard time seeing a pedestrian and they're going to be exposed to high kinetic energy. And those situations are ones that you might encounter in rural transition zones. And that's why I think this is important as well. So this sort of just affirms some of what we've been seeing on the previous slide, where we do really see the losses in safety and the big risks nowadays are in the pedestrian and cyclist injuries in the United States. We also know this is some of the work that's been done in New Zealand. I saw my friend Shane Turner is in the chat. He has been involved in a lot of the safe system approach work in New Zealand, so happy to see him here. But we have a good assessment of, how fast people can go and still survive crashes. There's been a lot of research that has shown that as long as you are changing the intersection angle and reducing the speed, rear end crashes are pretty safe nowadays. You see tables like this where you see, as long as you're sort of changing that impact angle and reducing speed, that kinetic energy is not going to exceed injury minimization. So, where we do still have a lot of problems is a lot of the research has shown that pedestrians and bicyclists have, around a 10% chance of fatality at even very low speeds, like 18 miles per hour. And I've even seen some studies that have shown that people have been killed by a vehicle going about 5 miles per hour. So it is definitely the kinetic energy burden is definitely borne by pedestrians and cyclists. And I think it's just super important that we reduce our kinetic energy through designing self-explaining roads. We also know that vehicle design has changed quite a bit over time. Our vehicles have gotten a lot bigger, and because of that, there is more kinetic energy, especially as people drive faster. And I would argue that's one of the big drivers of pedestrian fatalities today. So to go back a little bit to speeding behavior, when we do not design roads that are self-explaining, we are not activating those human factors that can keep people safe. So for those of you who are engineers, you've probably seen graphics like this quite a bit. As you go faster, your visual senses sort of dilate and it becomes much harder for you to see the surrounding roadway. This could really be important in a rural area, like around a rural transition zone, where maybe you are suddenly going to have tractors or children, someone out on a main street in a rural town. You want to be able to have people slow down and be able to see who is around them. We also know that people need a lot more time to slow down depending on the speed that they're driving. And this could be very important for, again, rural transition zones if suddenly you have traffic appearing in front of you. I will note, I've been talking about speed generally. This is a little bit of a challenge in the United States in that most of our crash statistics do not report speed as the factor, but rather speeding as the factor that was involved in a crash. Now some do, but often the speed is only estimated if it was an older crash. I know some vehicles have the traffic data recorders now, and there is some interesting data that's coming out of those black boxes nowadays. But a lot of our crash data largely focuses on speeding. But my argument would be that even what is legal for speeds is not always safe. And we know that speeding as kind of an X factor crosses over with a lot of other risk factors, such as alcohol use and lack of restraint use, and just raises the risks overall. We know that maybe a third of fatalities involve speeding. I would argue that the actual number of fatalities the actual percentage of fatalities where speed was a factor is probably much, much higher than about a third. And so all of that, I think, should take us back to this point. If we understand that people often do not consciously choose the speed that they're going to travel to, if they're not intuitively if they are intuitively making decisions on a roadway instead of deliberating how to drive faster, then I think we need to come back to this question of how do we design self-explaining roads? And so some of this that I would argue is that we need to make sure that speed limit and that context match and that we fit into those three categories. And actually, one of the examples that I really like from a state DOT that provides some guidance on this is to look at the Florida DOT's design manual, because they identify if you are designing a roadway that is in a rural area, say a rural town, and you recognize that you need to hit 25 miles per hour, it gives you an entire menu of options that you can take to get down to that 25 miles per hour. So you can do things like roundabouts, lane narrowing, horizontal deflection, speed feedback signs, rectangular rapid flashing beacons. All of these things are appropriate and can help you achieve a self-explaining road. But what I'd also argue is that we need to get away from just doing speed countermeasures and actually be thinking about how it is that we build our roadways themselves in order to have these transition zones. So I wanted to look at a rural highway that I used to drive on quite a bit when I lived in Lubbock, Texas. And I don't know if anyone from here is a Big 12 football fan, but Texas Tech, the first time ever winning the Big 12 championship, was kind of excited to see that. Texas Tech and this rural area of Lubbock may be more on your radar than it used to be because of how they did. But this roadway leading from Lubbock out to Slayton, this was an example of where we had a two-lane highway. I believe it was signed at 55, maybe 70 in some sections, and then suddenly you're driving into a rural town. And this is definitely an area where I would say this is dangerous, right? So what we need to think about is how are we making this a self-explaining road? How are we making this transition intuitive? Can we apply visual friction on the sides? Can we maintain the barrier and reduce the number of lanes? And can we add some visible signs or gateway treatments? And so again, we need to not just tell people to slow down. We need to think about changing that environment, and maybe even doing things like a roundabout at those intersections leading in to get people to slow down, because it is connected to speed is connected to so much. And we know that reducing visual friction, so things that are going to cause people to go faster, wide setbacks, multiple lanes, and wide clear zones, whereas things that are going to cause people to go slower, having street trees, flex posts, or narrow lanes, dense developments, all of these you can may not be applicable in rural zones, but we can think about narrow lanes, flex posts, street trees. We can think about maybe other sort of aesthetic treatments that can actually just guide people to slow down naturally. And a really interesting application of speed management that popped up recently. This study was done by IHS and partnership, I believe, with Governor's Highway Safety Association in Maryland. I don't know if anyone from this call is from the area, but one thing that they did that actually made the road more self-explaining was they just painted wider stripes in the middle. They actually found that increasing that stripe thickness on this roadway actually got people to slow down, which I think is amazing. It seems like a really simple change, but it somehow made our roadways more self-explaining. But to get back to some of these transition zones, again, if we're thinking about the fact that we want more discrete roadways that are designed to transmit from a freeway or a large highway to local access, we need to be thinking about things like these welcome signs, like these delineators, like things that are going to be causing visual friction, like the trees, in order to make this much clearer that this would be that transition zone. And doing this will help us get down to the safe system pyramid. I heard that David Ederer was around this morning, so happy to hear about that. But doing these kinds of things help us get down to these larger built environment factors that can have so much more impact than just trying to tell people and get them to make more deliberative decisions about safety. So, in conclusion, our roadways are often not self-explaining in the United States, and we overestimate how intuitive our roadway designs are. And because of that, we design roadways that lead to speeds that kill people. And we can address it by better understanding human behavior and looking for ways that we can design our roadways to be self-explaining through those menu of different options, through increasing visual friction, through doing things like even just increasing the thickness of the paint on the roadway. And with that, I am going to wrap up, and I believe we're passing it over to Jeff. Thank you all for chiming in the chat. I really enjoyed seeing your slide or your comments.
Thank you so much, Wes. And we have a slew of questions for you. So we'll ask just a few right now, and then we'll move along to Jeff, and we'll come back to any remaining questions we have after.
Okay.
The first one that we have for you is, what about the concept of the shape of the landscape that the road is constructed on? Couldn't this also offer self-explanation for the road?
Yeah, I really appreciate you bringing that up. I maybe didn't hammer that point quite as much as I should have, but when I was showing the slides or the slide from the FDOT roadway design manual, they actually, mentioned this point that you need to pay attention to what your context is when it is when you're trying to get these self-explaining roads. So we need to have good synergy between our roadway design and our land use. We don't want to have really high speed roadways where we are also asking people to make a lot of access to nearby developments. A big issue that happens in a lot of places that maybe were previously rural that become suburban is that you might have like a large high-speed roadway that suddenly an apartment complex or a commercial area gets developed next to that roadway, and suddenly you have pedestrians trying to cross the street, whereas you still are facilitating a design that causes vehicles to go at 55 miles per hour. That's a really risky environment. So I think part of, as the question raised, part of having a self-explaining road is going to be making sure that our land use facilitates that discrete type of roadway.
The next question for you, the asker says that all roads self-explain what speed they want you to drive at. And they're wondering if the real question is whether the explanation meets the goals of how we need drivers to drive. For
Yes.
example, in a school zone, we ought to design the road to protect the youngsters. How do we do the explaining without making driving more difficult?
Hmm. That's a good question. And I would say yes. To the first part of the question, yes, I think we do design roads that are intuitively leading people to some kind of speed. So people are going to drive at the speed typically that the road is designed for. Unfortunately, we get into conflicts again where we have these mismatches between the function and the design. so things like, having a lot of school zones on a larger roadway is going to lead people to going faster. As far as the second part of that question goes, of how can we make uh, these self-explaining designs less difficult for drivers, I think having a credible speed limit that matches the roadway is going to be one way that you can do that. Um, I I will say I will push back on the idea that lowering speed limits alone is not sufficient. There's actually been a good amount of research that has shown that just decreasing speed limits can be beneficial. But I'd also argue that if people find a speed limit non-credible, it's probably because we have designed the roadway to facilitate a higher speed limit. So I think part of it is making sure that we have a speed limit that matches the roadway. But to give maybe a bit more of a challenging response to that question, and maybe something that is harder to do in rural areas, and I want to fully acknowledge that, is that I'm not sure that we need to always make driving easy. And I'm going to draw on personal experience here for this response. When I was in Sweden a few years ago, I spent a lot of time in Gothenburg, and one thing I observed is that that town actually makes driving very difficult for people. There are constant crosswalks, there are constant intersections. If you are in a car, you are constantly coming up against transit. And that kind of is designed intentionally to deter people from driving. Now, if you're going to do that kind of thing and you're going to make it difficult to drive, you have to provide a healthy alternative. Or something like transit options, a lot of buses. You have to provide something that is going to meet the same sort of need that people have for getting around as maybe being in a car. Um, I think maybe in a rural area, again, we probably don't have access to a lot of buses in rural areas. I know there's a big concern with even just getting paratransit access out to people who can no longer drive themselves. Here in North Carolina, we have a rapidly aging rural population, and a lot of those folks, as they can no longer drive themselves, become reliant on paratransit. So transit alone isn't probably a solution for most of the country, but maybe this leads us to think about what needs can also be met through, say, increased bicycle facilities or better, pedestrian facilities. Are there things where we can get people out of their cars and maybe being active and engaged in order to sort of find solutions that work for them? So, sorry, kind of a long answer to that question, but I would say, I guess, big picture, I think we need to design roads that are intuitive, that lead people to a speed that makes sense. But we also need to also come up with alternatives to driving, I think, to make our roadways safer.
Another question that I'm interested in hearing this as well. Someone asked if you know of any AI creative tools that are available for demonstrating or exploring potential physical changes that can make existing roads self-explaining.
Ooh. I don't actually. That is a very good question. I would welcome if anyone in the chat does. I don't off the top of my head.
Okay, and one last question, and then we're gonna switch over to Jeff. This last one is there anything to be said about minimum speeds? As someone who commutes 25 to 30 minutes to work every day, I find myself coming across people who are going well under the speed limit, even if conditions are favorable, and often feel like it poses a safety risk for me and those around me traveling at or near the posted speed limit.
Hmm. There was a fair bit of research. Well, sorry. For many years, this question of speed differentials is kind of what this question of minimum speed limits is getting at, was actually sort of a big topic in the speed and safety research. A lot of people pointed to there being a large speed differential as something that caused a lot of risk on a roadway. Um, I think maybe the speed differential is a bit of a red herring, in that I think if you have a self-explaining road where the speed limit and the roadway context match each other, you're probably going to get less of that problem. Um, I think where we do have just really high speeds that facilitate, or sorry, roadways that do really facilitate high speeds, but maybe we're also granting access to slower vehicles, or not providing the kinds of facilities that tractors are going to have to drive on. I think maybe that's where we are going to get some of those issues with speed differentials. So While I do think it is possible that speed differentials could cause some issues, especially if there's a lot of weaving behavior, I would say maybe we need to get at the roots question of why people are driving slow and fast on the same roadway.
Perfect. Thank you again for answering all of those questions, Wes, and for your presentation. You did a fantastic job.
Thank you.
Next up, we have Jeff Pulver. He is the Assistant State Traffic Engineer at the Maine Department of Transportation. After graduating from the University of Maine in 2017, he spent a year and a half as a consulting engineer, focusing on mobility analysis, traffic engineering, transportation safety, and highway design. He joined Maine DOT in 2018 as a safety engineer in the Office of Safety and Mobility, where he served for 4.5 years. In this role, Jeff led network screening and concept plan development while also contributing to alternative analysis and other safety initiatives. From 2023 to 2025, he served as Maine DOT's Director of Research and Innovation and just transitioned into his current traffic leadership role this month. And I'm very excited to turn it over now to Jeff.
Thank you very much, Jaime, and both of you, wonderful presentations. Yes, as she mentioned, I'm the Assistant State Traffic Engineer now, and I'll be talking about something that I worked on when I was working in safety a few years ago. That's been very exciting for us, that we've had a lot of chance to implement and see in action since we started working on it. One thing I want to bring up is Jaime, during her presentation, mentioned the systemic safety improvements and getting to intersections before crashes happen. I think that's a really important part of crash strategy, safety improvement programming. But there's always a portion of your program that should go towards fixing the locations which have had the worst performance. And what I'm going to be sharing today is about how do we find the locations that have actually been performing the worst, that have the most kind of proven risk of fatal and serious injuries happening, because we have strategies nationally to do that, but I feel like some of those strategies have maybe not met our needs, especially with the safe system approach and its implementation in the US. So what have we done? We've created an evaluation and screening process which aligns closely with the safe system approach, and as mentioned multiple times, we incorporated principles of kinetic energy. And to me, the cool part is seeing how those kinetic energy kind of calculations align with our actual crash data at Maine DOT in the state of Maine. And then we're using this information to rank intersections and prioritize them for safety improvement based on their likelihood of a fatal or serious injury happening. So what I have is going to talk a little bit about crash forces and kinetic energy theory, and I can go through that a little bit quicker because it's been covered so far, and then show how this information applies to real scenarios in Maine based on real crash data, and then explain the process that we're using to rank these locations and some of the tools we've developed, and then finally show a little bit of performance metrics about how well this has been doing since we started implementing it. So we've heard a lot about the safe system approach today, as well as the humans have a limited tolerance to crash forces and the impact of speed on kinetic energy and crash severity. But look at this this figure to the top right of the screen, and many of you have probably seen a variation of this. This shows, based on safe system approach research internationally, how different types of crashes are their likelihood of a fatality change based on impact speed. And two things that you can get from this really quickly is that speed has a tremendous impact on the likelihood of something leading to a fatal crash. And also, another thing that I think gets somewhat glossed over when it comes to network screening and other crash analysis is the speed that influences these different crash types is quite different for the different crash types themselves. So a lot of the work that we've done here has been separating the data by crash type and then analyzing those individually, then aggregating it up afterward. So looking at the theory of crash forces, we saw earlier conflict point diagrams and the focus on the three different types of conflicts you see here, the diverging, merging, and crossing conflicts. And those crossing conflicts are those white dots near the center of the intersection. And as Jaime mentioned, I think you have 32 conflicts here, and many of which are crossing in a traditional intersection. And then at a roundabout, you have much fewer conflicts, none of which are crossing. And we've known anecdotally for a long time that these crossing conflicts, which are close to a right angle, are worse, but actually putting some numbers to that and using that quantitatively in our processes is what we've been working on. I went to the National Safety Engineer Peer Exchange in 2019 in Minneapolis, and we had a speaker, Dr. Blair Turner from Australia, and these are a couple of his slides here showing the kinetic energy, which is represented with the red plot on the right side for these two different intersections. So we have a traffic signal with a bunch of lanes and a bunch of right angle conflicts. And then we have a roundabout at the bottom with similar number of lanes. And you can see the roundabout has way lower kinetic energy than the other one. And I think looking at this in the US, having less experience with this, it makes sense, but it's still somewhat mystifying about what this actually means and what we can do about it and how we can incorporate that. The first thing you learn in physics is force equals mass times acceleration. When you think about that for two vehicles hitting each other, the mass part is obvious. The acceleration is really the deceleration or from the speed a vehicle begins with, and then the time it takes or the deflection distance to get to the resting point. And that's a factor when it comes to hitting the side of a vehicle. Think about how much is that vehicle designed to deflect versus the front of the vehicle or the rear of the vehicle or other areas. It's obviously designed pretty rigid so the passenger or the driver doesn't get completely crushed. So a lot of the force is really absorbed by the occupant of the vehicle when you're hit on the side of the vehicle. And we see that show itself in the fatal and serious injury statistics for side angle impact crashes. And I don't need to get into this much. It's already been talked about quite a bit. But kinetic energy, you see that the velocity is not a linear relationship with kinetic energy. It's a square relationship. So as velocity goes up or speed goes up a little bit, the kinetic energy can go up a lot. And we'll get into specific examples of what that actually looks like. And of course, kinetic energy has been mentioned in International Safe System Resources as closely tied to fatal and serious injury likelihood. And we've seen that very close relationships based on main data. So here's two situations. This is like taking you back to college. We've got vector diagrams, looking at the blue vehicle arrow going up on the screen, hitting a yellow vehicle going left with that yellow arrow. So we've got on the left side, we've got a 25-mile-an-hour car. On the right side, we've got a 35-mile-per-hour vehicle. And you can easily see that on a roadway, vehicles driving 5 miles per hour different. When you look at this, the speed on the right is 20% higher, which may be more than you intuitively think it is, but the kinetic energy is 44% higher. So just a little bit of speed change on the same type of road can make a big difference in the kinetic energy, the forces present. Now, on a more extreme situation, we've got a 25 and a 55 mile per hour collision. The speed is 2.2 times higher. The kinetic energy is almost 5 times higher in that situation. Then what about impact angle? So bring you back to relative velocity, right? Vectors, again, get to the relative velocity. How much of this speed is actually going into the direction of the yellow vehicle? And if you have a 30-degree angle, like a merging conflict, only half of that speed is actually going to the direction directly into the yellow vehicle. So the relative speed is twice as high on the left as it is on the right. Now, if you put those two theories together, we've got a merging conflict at a low speed and a crossing conflict at a high speed. This turns into very different forces. And it's intuitive, but putting some numbers to it can help. So the crash on the right has almost 20 times higher kinetic energy going in the direction of the yellow vehicle. And that actually aligns pretty well with crash data, which I'll show you. So how do we apply this theory to the crash data itself? So the first thing that we did, even before we got into the weeds of this effort that we're doing right now, is probably 5.5 years ago, we looked at our whole data set of intersections in the state of Maine, and we broke down the quote-unquote angle crashes, or what we have intersection movement crashes in the state, which could be left-turning crashes or right-turning crashes, or crossing conflict crashes, but it's crashes that are happening in the intersection. And we broke those down by primary road speed limit. And what we found was every 5 miles per hour, the speed limit went up. The injury percentage went up, as well as the fatal and serious injury percentage, and the KAB, so minor injury or worse crashes. All of those metrics went up when we looked at the whole entire state for every 5 miles per hour. And that's not to say that just by changing the speed limit sign, you may see a huge difference here. And maybe someone is going faster on a 30-mile-an-hour road than an individual 35-mile-an-hour road. But over the course of the whole entire state, you would generally see each one of these locations. You'd have 35-mile-an-hour roads. People are going a little bit faster than 30, so on and so forth. So we started using this and bringing this to towns when we were looking at high-speed angle crashes and proposing solutions and saying, hey, maybe you had 2 serious injury crashes here, but based on this data, you're actually lucky. Based on the crashes and the typical rates we see, we actually should have had more here. And we started to ask some questions of, could we implement this on a wider basis? So does the severity of other crashes change with speed? How do these results change based on intersection control? So what about roundabouts and traffic signals and always stops? We've done a lot with always stops in Maine, similar to North Carolina in the last 5 years. So how does the risk compare across intersections with different crash patterns and different speeds? So how do you compare a location with 5 angle crashes at 50 miles an hour to a location that's 30 miles an hour with 2 pedestrian crashes? And which one is worse and which one should be prioritized higher than the other? So we've worked on that and built a system where we can kind of quantitatively put that all together in one place. So a connection between kinetic energy and KNA percentage. We calculated the fatal and serious injury percentage for basically all our intersection crashes in the state. We just look back at crash data, a really long history of crash data, in most cases 10 years of data throughout the state. And in ped and bike situation, we have limited data, so we went back a full 20 years. And we basically put things into bins by crash type and by speed and intersection control. So we controlled both the primary road speed limit. We didn't have actual speeds, but the speed limit is enough to kind of get you started with this. And then we separated the always stops, the roundabouts, and the traffic signals, and then put everything else in one big combined bucket. And we were able to adjust based on crash angle, and I'll get into that next. So how do you account for crash angle in the data? So for those who haven't dug into the weeds of crash data, and it's a little bit different state to state, but within a crash, you have the crash level data, driver level, like driver action level data, and then you have vehicle level data. And in Maine, within each vehicle, we have a most damaged area category that the police have to fill out for every single crash, for every single vehicle within every single crash. So we looked at, started with 5 years, eventually went up to 10 years of our intersection movement crashes and said, okay, how many of those, because the most damaged area, it goes into a bunch of different categories. So you can have front passenger side, you can have passenger center, rear driver corner, all those different things. I said, okay, let's take the percentage of these that's actually the most damaged area on one of the vehicles in the angle crash is front. And that'll be a placeholder for they hit at pretty close to a right angle if the most damaged spot is the middle of the front of the vehicle. And I wasn't sure how many would actually be coded that way. You never know until you look at it. And it was about 53% of the intersection movement crashes were coded that way. So we said, okay, those ones are right angle, binary, and the other ones are not right angle. And when we split it up that way, it was a huge factor in the fatal and serious injury percentage of the crashes, the crash severity. The frontal crashes, frontal impact crashes were almost 4 times higher likelihood of leading to a KNA. So we decided, okay, we immediately know we need to start working this into our screening method to consider the risk that's going on with the crashes. And we had some other corrections. One of them was always stops, and this gets down to treating the high risk crashes. If you think about an always stop, we've been doing a lot, as I mentioned, and our biggest worry with them when we put them in is, are people going to be able to see the stop sign and stop at it? Because if everybody stops at a stop sign and then starts and they hit each other in the middle of an intersection, they're probably going to hit each other at 10, 15 miles per hour. And I have pretty low worry about that actually turning into a serious crash. But if someone blows through the stop sign and hits at 45 miles an hour, then we've got a similar situation to a free-flowing approach. So we found that when people run the stop sign at those, which is a driver action, in the police data, it's over 6 times more likelihood than leading to a KNA than the ones that don't. So we started to incorporate that into our system as well. So getting beyond theory and digging into like actual crashes, these are pictures of crash reports at actual intersections in Maine. So we've got the low speed situation is 25 mile per hour. It's in the other intersection control bucket. And most of those are minor road stop control. This one's actually a little bit unique, but it's another intersection control. It's not signalized. It's not roundabout. It's not always stop. So we've got a merging conflict on the left, a left turn into a lane. So that's pretty close to that 30-degree angle there, but it's a non-frontal impact. It's not a crossing conflict. Then we've got at the same intersection on the right, we've got a true right angle crash, someone crossing at nearly a right angle and impacting each other. And what we found from our data, and similar to what I just mentioned on a previous slide, is the crash on the right has about a 1.8% chance of leading to a fatal or serious injury. The crash on the left is about a 0.5% chance, and that's 3.6, 3.7 times more likely to lead to a KNA on the right than on the left. And if you take this in the bigger picture, we've got that same, low speed merging conflict crash on the left, and we've got a high speed right angle 55 mile per hour crash on the right. And the crash on the right has over a 10.5% chance of leading to a fatal or serious injury based on that main data, which is just over 21 times more likely to lead to a fatal or serious injury than the one on the left. If you remember back to those vector diagrams, those two scenarios we looked at were it was 19.4 times higher likelihood. So these are actually very, very close to the kinetic energy changes between those two. And especially for angle crashes and the crash angle and the speed for intersection movement crashes, it's an extremely close correlation between the kinetic energy difference and the likelihood of fatal happening. And then looking across different crash types. So this is an intersection in an urban area of Bangor, Maine. And this is a crash diagram on the right. And the first thing you see, traditional traffic engineering, you'd say, okay, there's all kinds of rear end sideswipe type of crashes here. And the traditional method would be the best way to make it safer would be to reduce the type of crash that's most frequent at the intersection, which would be the rear ends. There is one pedestrian crash here. So the question is, how do the risk of all the different crashes we have at this intersection add up, and what is the greatest risk here that should be focused on to improve safety? So we have 13 rear end sideswipe crashes here at a signalized intersection. This is a signal. Our data across a lot of crashes across the whole state, that's a really low risk crash type. It was 0.21% chance of leading to a fatal or serious injury. This 25 mile per hour intersection pedestrian crashes were almost 17%. So that one pedestrian crash has over 6 times higher risk of leading to a KNA than all those other rear end sideswipe crashes combined. So once you start to get down into the weeds of what's the greatest risk at an intersection and what countermeasures should we be working on, sometimes this could be a helpful tool that way, but really we're mostly using it in the screening method itself. So getting to the screening method, we called it KNA potential, but it's just our kinetic energy risk based on actual crash history in those factors that I mentioned already. So we did have, why create another screening method? We had a few screening methods that really weren't meeting our expectations. We had a high crash location rankings list, which was really based on 8 or more crashes in a 3-year period, and something called a critical rate factor greater than 1. So that's a crash rate compared to the crash rate at similar intersections throughout the state. And there's nothing in there about crash severity or crash type or speed or any of those things. It's really kind of a crash frequency and crash total metric, and it's been around for many decades. People are used to it in the state. We around 2015, 2016, I think we put a highway safety manual screening. This was a little bit before I got to the safety office, and we have network screening level, AADT, some CMFs built in there for left turn lanes and other things like that. It calculates the predicted crashes and then calibrates that based on 3 years of crashes at the intersection, correlates that to crash costs, and then finds the excess cost, the difference between the expected costs and the predicted costs. All of that still, the observed data that's put in doesn't consider the way we made it, the way Maine has it, didn't consider the crash severity of the observed crashes, and it only looked at 3 years. And I'm seeing a lot of limitations when you're only looking at a few years of crashes. You're not getting the whole picture out there. And I know the push for that is that, things change at an intersection. If you look back too far in the data, you're going to see things that aren't relevant anymore. And in practice, I don't think that that's as common as we want to believe it is. But the HSM models also in Maine anyway, they become a poor fit for the true outlier intersections. They're designed for the typical intersection or across our 30-something thousand intersections. It works pretty well. But the problem is our worst of the worst locations are all outliers, and the crash rates and the injuries and all of that stuff are way worse than any of the models could ever predict. So we needed something better at those outlier worst locations to prioritize them and figure out what the true level of risk was. So this KNA potential that we came up with, it's our estimated number of fatal and serious injury crashes we would believe would happen over the next 10 years. Big assumption if the current crash patterns were to continue. And also, it's another way of looking at it is a ranking of the intersections where fatal and serious injuries are most likely to occur. So at a basic level, we look at a couple of things. We look at the crash patterns that are there, and then we look at the actual fatal and serious injury crashes that have happened over a long time period at the intersection. And we use that as kind of a straight face test calibration to incorporate that and not just have the theoretical severity. So how do we quantify the crash patterns? We talked about that a little bit, but it's different than everything else, but it's pretty statistically naive. We just go into all those different ways we divided crashes at an intersection, and we say, okay, multiply that type of crash and the number of them at the intersection by the percentage chance that leads to a fatal or serious injury. We looked at the 5-year crash history for most crashes. If for ped and bike, which are less frequent, we looked at 10 years. We convert that all to a per 10-year time frame and then add up the risk. So for example, if something had a 5% chance of leading to a K or A crash, we would call that 0.05 KNAs, and we do that for every crash, sum it all up, get one big number. And that was kind of a sub-metric we call it the crash pattern potential. And this is a more detailed way to do that if I had more time and get into it. Then we have the other part of that, it's the KNA history. So we call this the weighted KNA history because we're intentionally building in a recency bias where we want to consider fatal and serious injuries that have happened here over a very long time, but we want to consider the more recent ones in a greater quantity. And like I said, this is really our straight face test. So when we look in Maine at our locations with the most KNA crashes at a single location, as Jaime said, in rural areas, they're really dispersed. So we are a very rural state. And when you add it up, the 5 years, we only have a few locations with 3 KNA crashes at one location, and then it drops off. But if you start to look at more timeframes, they start to identify themselves more and more, look at 10 years, look at 15 years, look at 20 years, and the outliers really start to introduce themselves. And then you get to the situation where you've got 4 KNAs over 10 years, and no matter what the crash pattern says or the other metrics, when you have that many, you shouldn't be shocked when a 5th one happens. You have a trend in itself that there's severe crashes happening here, and we should be incorporating that into our strategy. So we built in the recency bias where the ones that have happened in the last 5 years count the most, the next 10 years count a little bit less, and then the ones that are between 10, 11, and 20 years count half as much as the recent ones. And there is some situations where those old ones do become irrelevant, but we're finding in Maine that that's not the case most of the time. And I've gone to towns and I've brought them safety data and talked about an intersection, and they tell me about a fatal crash that happened 8 years ago or 11 years ago. And I can't look at them with a straight face and tell them that that crash is irrelevant to our analysis, because it's not. And we've tried to do that before, and I've left thinking, we're wrong. Something's wrong in our process. Nothing substantial has changed here. Maybe we've trimmed some brush. Maybe we put in a different static sign, but nothing that has gone far enough to make that old fatal and serious injury irrelevant. Unless you're going in, you're changing the traffic control or the fundamental, cross section of the roadway is changing. It's hard to throw those old ones in the trash. And I think that's what a lot of our models do. So then we combine these two things together. So again, this is, somewhat anecdotal. We played with this percentages a little bit, but it's not based on optimized research to get the best result. And I think there is a lot of potential to build on this work we've done with greater statistical analysis research if they're approaching it in the right way. But what we have is the crash pattern count 3 times more than the weighted KNA history, and we had a different percentage, and we changed it over time to engineering judgment to have it fit the best way. And this allows us to chase the fatals without one fatal crash or serious injury crash, shooting something so far up the ranking list that we become overreactionary. And what happens is when we look at our top ranked locations, most locations will have both very concerning crash patterns with high kinetic energy or with ped and bike crashes, as well as actually a serious injury crashes in their crash history over the last 10 years, over the last 20 years. So almost all of them have both of those things, at least in the top ranked locations. So this is like the breakdown of the different qualities, different attributes of the locations. So our KNA potential, you can see the rural locations, the traffic signals, the roundabouts. Clearly, our 2 old processes were not identifying the same locations at all. They were quite different along those locations. But the top right, I'll point out, 91 out of the top 100 locations were either high-speed right-angle crashes were very common, or ped and bike crashes are very common. 2 of the highest, risk types of crashes. So just quickly, here's like a quick snapshot of our ranking list. All these green ones are all ones that we've either programmed work or actually have solutions that have gone in place. And there's a lot of ones that were high on this list that the safety office has knocked out and put solutions in the last handful of years. We're working our way through this. And one thing you'll notice is this bold column, the KNA potential. You see the top ones are around 3.5 KNAs over the next 10 years is our estimate, and it drops off actually pretty quick. Even in this top 30, you get it down to about half of that. And in general, that's a trend that we see across this is that our risk is a little bit top heavy. We have around 34,000 intersections in the state, and a high percentage of that is in the top 2,000 and the top even 300 locations. We created a dashboard, a GIS, a tool where we can enter our node and get a whole bunch of attributes. And this is something I really love that we did. We created a severity comparison tool where, based on the main data and some kinetic energy theories, you can plug in the the type of intersection control, the speed limit, and the crash type, the angle of the crash, and it'll show you compare crash A and crash B, the fatal and serious injury percentage, the crash cost per crash, and the kinetic energy between the two. And it's a little bit uncanny sometimes to see how closely the kinetic energy aligns with those other metrics. And one thing that we hear is, okay, those are crashes from the past. That's the past. That's somewhat irrelevant to the future. What does that mean for the future of our location? And what we found so far is it's actually a pretty good indication of what's going to happen going forward. We did this data in 2022 and before, and then we let the next year happen. We said, okay, none of this data from the next year is going to be going into this. We're going to test and see how well it performed on the future after we made this model begin with, and we're updating it annually. But our prediction across the whole state predicted 180 intersection KNA crashes. We actually ended up with 170 the year after, which is a little overestimating, but not by a huge amount. And then when you look at the distribution across our top rank locations, we had pretty close. So like our top 10 accounted for about a 1.5% of the KNAs, which is pretty close to our estimate. Top 100, we predicted the top 100 locations would add up to 9% of the total KNAs, and those actual specific locations added up to 8.2%. And those followed along like very closely. So I feel pretty comfortable with it. We created some metrics to test it against our other methods. We looked at where those locations were, where the KNAs happened, and where the KNA-B crashes happened, just because it's a larger sample size, and compared to the rankings in the different systems to figure out which ones were ranking those locations where they actually ranked the highest, as well as we looked at the top 10, top 25, top 100, top 300 in the ranking list and said, okay, how many KNAs actually happened here? And based on all those metrics, this new method it won almost every single category against our older previous methods. And we'll say other states may have better HSM screenings than we did, but this one dramatically was outperformed by this new kind of somewhat simple metric. So we did find it's a really good indication of future risk based on looking at this crash methods in the past. Other things we've been doing, we worked with Federal Highway, and one thing I want to point out is from rural states. That's an intersection behind us in a small town called Waldoboro, Maine. On the mid-coast, they had two locations that were relatively low volume, that didn't have a lot of crashes, but their crashes were high-speed right angles, and some of them had either a fatal crash or a lot of serious injury crashes. And in traditional methods, these were not showing up as anything we should ever do an improvement on. But through this new method, we were able to justify that these are actually pretty high-risk locations. We went out, we put in all-way stops at both of them. We made some sight distance improvements, and those were actually the two greatest concerns from the town for a very long time, and they could never get the support to get them fixed, and we were able to fix them. I go through them all the time now, and they work very well. And some of the other things we want to do, we want to improve and automate the data. I have to manually update it right now, which doesn't take that long, but we want to integrate it more permanently into our system and get it out there easier for people to find, our practitioners, our consultants, so on and so forth. And like I said, more research from others is big. And then for implementing it elsewhere, one thing I want to emphasize is most of the work we did on this, I did in a little over 2 weeks. I mean, we had the data, I just downloaded it, locked in, added everything up. Like one thing I'm saying here, don't let perfection get in the way of good or better. I mean, this is better than the systems we had before. And if we were trying to get it perfect and develop advanced statistical modeling, it would have taken years to even figure out what we had here. But we calculated it, we added it up, and we started to roll with it and make improvements right away. And another thing is crash angle is a big factor.
but that's the hardest part to get. So if you can start without that, you're still getting something good. So it's, like I said, just start and don't overthink it. And thank you guys for the opportunity to share this today. I'd be happy to talk about this more with anybody who has questions.
Wow, thank you very much. We've had a lot of information going on in the chat, a lot of questions in the Q&A. Unfortunately, we are out of time and do not have time to answer those questions, but we have provided you with contact for the trainers. If you do have questions and want me to reach out to anyone, please go ahead and send those to us at info@ruralsafetycenter.org. And we will get those out to the trainers as well. So thank you all for joining us. Thank you so very much to Jeff and Wes for those presentations. I know both of them had a lot of great discussion, a lot of questions. Everyone learned a lot, including myself. We really appreciate you taking the time today to present to our audience. Thank you guys also for joining us for all 3 sessions today for our virtual mini conference. We will have part 2 featuring the other 3 elements of the safe system approach coming up over the next few months. So look out for an email for us on when you can register for those 3. Thank you all and have a great day.